Good morning, afternoon, or evening. Welcome to Mr. Nice's Math Analysis and Trig lesson for the day. Today we are going to be discussing what is called the rational root theorem. So rational, right? Not irrational, it's rational. It's a very logical root theorem. Okay, so the rational root theorem. So why might we need a theorem like this? Well, we've been talking about roots and zeros and factors and been working with some higher degree polynomials and sketching quartics and quintics and cubics and quadratics and polynomials of that nature. So let's suppose, let's suppose you have been asked to graph a certain quartic equation. We will call it P of x, and we'll say it is 3x to the fourth plus 13x cubed plus 15x squared minus 4. You've been asked to graph that. Well, the problem is quartics can be tricky to factor. Unless it's got a common factor in there, like an x, that you can take it out and make it a cubic, and then maybe you can group it, or a difference of cubes. Quadratics are a piece of cake. We can always use quadratic formula if we can't factor it. Cubics get a little trickier. Quartics are nearly impossible. So the rational root theorem says that the factors of P of x, right, the factors of this, will have to be the factors of the constant term divided by the factors of your lead coefficient. So, and let me, before we go into working this problem out, let me explain why real quick. Let's take x squared plus 5x plus 6. Right, that factors into x plus 3 and x plus 2. Right, well, why? Because x times x is x squared, and 3 times 2 is 6. This last term here, these last two terms, I hope you understand they have to be factors of the constant, right? Because we are distributing in order to figure out what multiplies to 6 and adds to 5, right? So 3 and 2. 1 and 6 was a perfectly good option as well, okay? But that would not have worked for this case. So factors of the constant. Now, why is it divided by factors of the lead coefficient? Well, let's take this example here, for instance. 2x squared. And you know what? I'm going to have to create one here first before I can give you this one. So let's make this a 3 and a 2. So 2x squared plus 7x plus 6. So the 3 and the 2 came from the 6. Excuse me again, the 2x squared, the 2x and the x came from the 2x squared. Factors of 2x squared, what multiplies to 2x squared? 2 and 1. Now why are we dividing them? Well, look at this. When I go to solve 2x plus 3 equals 0, I have to subtract 3. And then, you got it, divide by that 2. So I have a factor of 6 divided by a factor of 2, a factor of the constant divided by a factor of the lead coefficient. All right, and that is why the rational root theorem, in the end, makes sense. Okay, so let's continue with this one here, and I think I can do something fancy on here. We'll split this into 2 pages. We'll leave that guy there. We'll scroll to the next page so we can still see him. And P of x, we're going to rewrite it onto this page. 15x squared minus 4. So we are now going to use the rational root theorem, RRT. It says that the possible rational roots, the possible ones, not the guaranteed ones, the possible ones, come from factors of the constant divided by the factors of the lead coefficient. So we call them P's and Q's. The constant is our P, and the lead coefficient is our Q. Right? Mind your P's and Q's. So factors of 4. Positive and negative 1, positive and negative 2, and positive and negative 4. The factors of 3. positive negative 1, and positive negative 3. So all said and done, my possible factors, my possible rational roots, I should say, are positive negative 1 over 1, so that's positive negative 1. Positive negative 1 over the 3, so that's positive negative 1/3. Now use the 2, 2 over 1 and 2 over 3. And now the 4, 4 over 1 and 4 over 3. So all said and done, I have 12 possible rational roots, right? 12 pairs, sorry, 6 pairs, which makes up 12 possible rational roots. So how do I determine if they're actually a root or not? Well, we have a factor theorem, which tells us if they're factors. We have the remainder theorem, which also tells us. So when I plug these numbers in, I should expect a certain result if it's going to be a root, which means it came from a factor. So when I plug these guys in, let's take 1 for synthetic division, synthetic substitution, I should say. Don't forget your placeholder is 0. If I get 0 as my remainder, then I can say it's a root. So bring it down, multiply at, I already see this is not going to work, right? I'm already at 31, so 1 is out. So we try negative 1, we try 2, we try negative 2, we try a bunch of them. Okay, go systematically. I'm going to cheat here. I know that negative 2 is a rational root. From there, we'll be able to do more stuff once we get 1. So 3, negative 6, 7, negative 14, 1, negative 2 there. Sorry about that. Getting a little ahead of myself. Multiply, add, multiply, add. At this point, I've now broken it down to a cubic polynomial. Okay? However, that is not groupable, right? 3 and 7 have nothing in common with 1 and 2, so it is not groupable. So, I can either go back up to my list and try ones I haven't tried yet, or I can create a new list because I have a new cubic polynomial that has possible rational roots. I'm going to create a new list just for argument's sake. A new list, factors of 2 over factors of 3. So I have plus and minus 1 and plus and minus 1/3. I also have plus and minus 2 and plus and minus 2/3. Notice negative 2 is another possibility. It could be a double root. Not a double rainbow, but a double root. So let's try it. My new synthetic is going to be the cubic, right? 3, 7, 1, and negative 2. I'm going to try negative 2 again. Maybe I'll have a double root. 3, negative 6, 1, negative 2, negative 1, 2, and bam. Negative 2 is a double root. So far, P of x, this quartic, is the same as x plus 2 squared times 3x squared plus x minus 1. Okay. From there, unfortunately, that is not factorable. Okay, you can try to factor it. I promise you it is not factorable. So you have to use the quadratic formula. So our roots are negative 2, which is a double root, and x equals opposite of b, plus or minus the square root of b squared minus 4ac all over 2a. So I get negative 1 plus or minus the square root of 13 all over 6. So I have 2 linear roots at that random spot. We're not going to go ahead and graph this. We're just showing you how to find the roots using the rational root theorem here. Okay, so notice this is considered an irrational root right here. All right, because it cannot be written as a fraction involving integer values. Right, a rational number is not just a fraction, but it's a fraction with integer values. Okay, so keep that in mind. This is -1 plus some random decimal divided by 6. Not rational. Alright, so in the end our rational roots are -2, and it happens to be a double root here. We'll have more examples tomorrow, practicing how to do the rational root theorem, but you've got a good taste for it now. Hope you enjoyed the video.